We are going to talk about one recent important finding from our research group. We have been working on perovskite materials, which are very important optoelectronic material, and about 1 decade back it was discovered. So the advantage of these materials are that they are solution processable. You can make all kinds of electronic and optoelectronic devices through solution processing. So main problem with this material is that they are not very stable in the environment with the moisture and heat. So we have actually taken one stable material where usually the performance in optoelectronic device is not so good. So we try to improve its performance through some engineering of using microprinting technology. So basic idea behind this work is that we have used plasmonic nanostructures through 2D printing and then improved the performance of photodetectors made out of the perovskite materials. Though these photodetectors are very important device for various kinds of sensing and security purpose. So even medical diagnosis also it is useful. So basically these photodetectors are usually done by conventional semiconductors, which are processed at very high temperature and very high fabrication cost. But here we used basically the solution process for the whole device fabrication, and that's how it is a low cost and improved device. So in this discovery there are 3 students. The main lead author is Devabrata, who has actually designed all the experiment and done most of the experimental work, while this Shirshendu has done actually simulation to support our experimental finding. So now Devabrata will explain further about the work.
Okay, so as we all know, the plasmonic nanoparticles through localized surface plasmoresonance enhance both the optical and electrical performance of the device. So we use the plasmonic nanoparticles array for our device fabrication. So first over the device we made the nanoparticle array through printing system. So this printing technology offers you can say scalable and cost effective solution for the device fabrication. Unlike the other deposition method, this also enables us placing the nanoparticle with precise location, and also it helps us in controlling the density of the nanoparticles. So also it adjusts with the flexible substrate, so that can be used for the next generation wearable devices. So for our final device fabrication we use the nanoparticle array, then we use our global system for the perovskite synthesis. Then after using some encapsulation layer, we remove this perovskite material with substrate for the electrode deposition and for the IV performance. So with IV performance, after using the silver nanoparticle with the plasmonic effect, we got very high performance parameter like responsivity and detectivity, and also the on-off ratio in compared to the reported results. So and also with that, one more thing, we get the cell biased performance in which the device can work without any external power supply, which is very much crucial factor for like remote sensing and where energy consumption is required. So with that we design our devices. The uniqueness of the work is the use of this 2D printing system for making the nanoparticle array. So you can see how we do the printing for the nanoparticle array through this printing system, and this is our schematic diagram of the fabricated device.
So basically I have done the simulation part, since the main motive of this work is to incorporate plasmonic nanoparticles over the perovskite devices, and so how these nanoparticles influences the performance of the photodetector, that I have actually verified with the FEM based simulation, which is the finite element method based simulations. So it's basically like describes like how the electric field that is influenced by the incorporation of the silver nanoparticles. The gap of the silver nanoparticles matters a lot, and at which gap and how the pattern actually gives us the high electric field at the surface, that is done through this simulation, that is the FEM part simulation. Thank you.